Hi, and welcome to the first in this series of videos on proof. Mathematical proof being an incredibly important, very powerful tool for any mathematician. So here we go. We're going to go through a number of different techniques that we can use. So the whole series will include something called proof by deduction, or proof by exhaustion, and then a proof by use of counterexample. And we'll go through each of those in turn. So this first video, we're just going to have a look at proof by deduction, which basically just means we're going to take a particular statement and manipulate it and adjust it and prove that one statement can be written like something else. So here we go. First things first, a little definition for you. If we've got a statement that we've got to prove, that's referred to as a conjecture, and the proof will basically take us in a series of steps from that conjecture through to a final statement where we've shown it's true for every possible value we can use. So here we go. Here's our first conjecture. It says the sum of two consecutive square numbers is always odd. So what we've got to do is algebraically prove that statement. Now, we might begin by trying different values. So say, okay, clearly 1 squared plus 2 squared is 5, 2 squared plus 3 squared is 13, and so on. But the problem with that is, of course, that you can't do every single possible value. There's another one, 234 squared plus 235 squared, seems to be working. But the only way we can prove it works for every single possible value is to try every single possible value, and obviously that's just clearly A, very, very time consuming, and B, just not physically possible, because obviously there's an infinite number of pairs we could try. So we need a different way of doing it. We need to be able to do this algebraically and justify algebraically why this will work for every single pair of consecutive odd square numbers. So what we're going to do is have a look at an algebraic version of what we've just seen. And the way to go about this is say, well, okay, let's call the first number n, and then the second number is going to be n plus 1, one bigger than the first number. What that means is we can take these two square numbers and write this process algebraically. So we've got n squared plus n plus 1 all squared, and obviously the next step would then be to multiply out the brackets, do a little bit of tidying up. And now the key thing to this one is if we just take the first two terms of that and say, well, you know what, let's factorize those two bits. So all I've done is taken these two terms and just taken the 2 out. What we can now say is that that statement there, 2 bracket n squared plus n plus 1, well, the 2n squared plus n, that bit is always going to be even, because obviously whatever value we have for n, whether it's odd or even, we end up working out what's inside the bracket, double it, that's going to be even. And if we know that bit is even, that clearly means if I plus 1 onto an even number, I'm always going to get an odd number. So what we've got there is a proof that for every possible value of n that we could have, that the sum of the two squareds are going to be, is going to be odd. And there we've done it algebraically without having to go through every single possible numerical version. So that was one way of doing it. There's others. I'm going to quickly go through another one, which is just a kind of more logic-based approach based on odds and evens. And it says, well, if we've got two consecutive numbers, whichever way around you do it, one has got to be odd, and the next one has got to be even. So if my first number was odd, my second number be even. But if my first number was even, then obviously my second one would be odd. We know that the square of an odd number is always odd, because odd times odd is an odd. Square of an even number is always even. Again, we know even number times by an even number is always going to be an even number. And therefore, whichever way around you do it, the squares, we're going to have one square number that's odd, one square number that's even, and an odd plus an even is odd. So therefore, again, we've got exactly the same result. We've just justified in the kind of logic type of a way that the sum of two consecutive square numbers is always odd. Now, there is a kind of a rider to this, which is we've used some statements up here, these ideas about odds and evens. Yeah, we've used these ideas here without having to prove them. But, you know, kind of at this level, we can take statements like that as being, we can rely on them. But obviously underpinning this is the fact that if these statements weren't already proved, they would need to be proved, and if they didn't work, then the other proof or kind of our method wouldn't work. So the whole thing is basically, like I'm saying, it's kind of built on foundations, and if you kind of find out that somewhere up here that a statement's not true for whatever reason, then the whole thing comes tumbling down. But we're fairly we're on safe ground with this. We know about odds and evens, and like I said, at this level, you wouldn't have to go back and justify those statements. You can take those as given facts. Okay, so what we just looked at there, two different ways of doing essentially the same thing. Other types of questions you might get that will pop up in an exam would be proving identities. So all we're going to do is start with one expression and manipulate it until you get the next one. So there we go. Prove that x plus y times by x minus y is x squared minus y squared. And that's our old favourite, the difference of two squares. And this one really is just a straightforward start off with what we've got on the left hand side. So we're going to start off with this and work towards this. Again, we can treat this, so let's just assume that this isn't here, start with this one and end up turning into that. That triple line kind of equal sign just simply means equivalent to. So what we've got is we take this pair of brackets here, multiply it out, we end up with this expression x squared plus xy minus y squared, and then we know that those two middle terms will cancel, and therefore we end up with the result that we're after, x squared minus y squared. All fairly straightforward stuff. Right, so in the exam you're going to get proofs in a whole different range of contexts, and here we've got one to do with vectors and a geometric proof using vectors, kind of similar to what you might recall doing at GCSE. So what we've got is a parallelogram, and we know we've got that vector there is 6a, that one's 6c. We've got a point here, m, that's a midpoint there. We've got a point P that we're told is 2/3 of the way along AC. And what we've got to prove is that OPM is a straight line. So standard stuff, like say, similar to GCSE, but kind of you might find them just a little bit technically harder at A level, but here we go. So we're going to find OP first of all as a way to start this. So OP in terms of vector, like with vector proofs, I always start off with what I like to refer to as a route map. How are we going to get from O to P? And the route I've chosen is from O to A to P. And we know that OA is 6A, and we know that AP is going to be 2/3 of AC, so 2/3 of that distance there, which means we've now got to figure out what AC is. So we need a route from A to C, and so that's going to be minus 6A plus 6C. So that's that bit there. So that's our AC. And now what we've got to do is just do a bit of multiplying out the brackets, a bit of tidying up. So we've got 6A plus minus 4A plus 4C, tidy it up, and then finally stick it in brackets. And you'll see why I've refactorized it in a minute. Okay, so that's OP done. Next thing I'm going to do is find PM. So that's the vector that takes from there to there. And again, I need a route. So my route that I've chosen is going to be from P to C, and then from C to M. Right, so PC, we know, is 1/3 of AC, so it's 1/3 of that whole distance there, or that vector there. So that bit there, you'll notice, is AC. So we've got 1/3 of that. And then from C to M, M's the midpoint, so it's going to be half of 6A, because if that one is 6A, that thing is 6A. So we've got plus 3A. Again, multiply out, tidy up, and we end up with A plus 2C. Now what we've got to do is justify, and again, in the exam, you've got to explain to the examiner you understand and you know what these results are showing. You can't leave it to the examiner just to look at two things and draw their own conclusions. You've got to be absolutely clear. So what we're saying is, well, we've got to prove that OPM, there it is a straight line. So we know that PM is A plus 2C. OP is, again, contains the same vector. So that one, this one here is a multiple of that one. So we're saying they're both multiples of A plus 2C. And so that means they are parallel vectors. But the extra bit, of course, is we can have two parallel vectors that don't make a straight line. But the fact that P is on both lines means they are a straight line, or the posh word is collinear. For this kind of proof, what we're going to do is make sure that, yes, we're identifying the fact that they're parallel due to the multiples of A plus C, but also there's extra statements in here as well that fully justifies it. And there's our proof. Clearly, OPM is a straight line. On we go. So these ones are a little bit on the weird side. So what we're going to do is start off with a statement. So here we go. Here's a statement. So we've got to prove that for all positive values of X and Y, we've got X plus Y over 2 is equal to or greater than the square root of the product. Now, the way to go about these is to start with that statement, unpick it, and rearrange and play around with it until you get to a mathematical fact that you know, and then from that mathematical fact, then effectively work back towards the result you want, which seems slightly odd, but you'll get a sense of what I'm going to do as we run through it. So here we go. So we're going to start with my statements. Let's do a bit of rearranging. So take the 2 over to the other side. And then what I've done is taken the 2 root x root y over to the left hand side. And if you sharp, you'll spot that this thing here can be factorized. And it can be factorized like that. So that's kind of x minus y times by x minus y, which is x minus y all squared. At this point, we've got to a fact, because what we've got here is a mathematical statement saying that for whatever values I have of x and y, regardless of how big they are compared to each other, that this is a squared bracket, and we know that when you square anything, it's always bigger than 0. So what we're saying is if x was bigger than y, this would be positive, square it is greater than 0. But if y was bigger than x, this thing in here, x root x minus root y, would still be negative, but when you square it, it would become positive again. So this is a mathematical fact that we know, we're sure of. So all we're going to do now is say, well, you know, we can use that mathematical fact to get to our proof. So all I'm going to do is basically rewrite it all, but the other way around. So here we go. So there's my mathematical statement. I know it's a fact that root x minus root y all squared is greater than 0, which means I can write it as 2 brackets multiplied together. And when I multiply out, I get those. You can see what's happening now. Now move it over to the other side. And finally, do the divide by 2. And we've worked from our mathematical fact and reorganized it and manipulated it. So we're saying down here, here's our statements that we've proved. Okay, job done.